Welcome everyone. We are going to learn CUDA. So what is CUDA? CUDA is something that turns GPUs into supercomputers. So think CPU speed, now multiply it by thousands. That's CUDA. So before we dive into the code, we need to understand the brain we are working with. Imagine you are running a giant warehouse. In the old days, you had one extremely smart manager. This is your CPU. He understands everything, makes perfect decisions, but there is a problem. He tries to move every single box himself, one by one. Now imagine the warehouse grows 10 times bigger. No matter how smart that manager is, he becomes the bottleneck. This is where CUDA changes everything. CUDA is like hiring 5,000 workers overnight. These are your GPU cores. Each worker is simple, not very smart individually, but incredibly fast at doing one small task. But hiring workers is not enough. You need a system to give them instructions, coordinate with them, and make sure they don't collide with each other. That system is CUDA. So CUDA is not a programming language like Python or Java. CUDA is a platform and programming model created by NVIDIA that allows us to talk directly to the GPU hardware using logic that feels familiar to programmers. With CUDA, we decide what work can be done in parallel. We decide how thousands of threads cooperate. We decide how memory is shared and accessed. In simple terms, CPU equals to great decision maker, GPU equals to massive workforce, CUDA equals to the manager's instruction system that makes the workforce useful. And the most important thing to remember, you don't use CUDA instead of the CPU. You use CUDA to offload heavy, repetitive parallel work to the GPU, while the CPU remains the coordinator. Now that we understood what CUDA is, let us talk about why this shift even happened. For decades, the CPU was the star of the show. Think of the CPU as the manager. It has a few extremely powerful cores. These cores are optimized for latency, meaning they are very fast at responding to one task at a time. CPUs are excellent at complex decision making, branching logic like if, else, sequential workflow, operating systems, and orchestration. This is why CPUs run your OS, your databases, and your control logic. But here is the limitation: a CPU is not designed to do the same math millions of times at once. Now enter the GPU. The GPU is not a manager, it's a massive workforce. Instead of a few powerful cores, a GPU has thousands of smaller, simpler cores. Each core is optimized for throughput, not latency. Throughput means how much total work can we finish per second. GPUs are incredible at repeating the same mathematical operation, processing massive data sets in parallel, vector and matrix calculations, linear algebra at scale. This is exactly what AI, machine learning, graphics, and simulations need. So the shift happened. At first, we used GPUs only as accelerators. The CPU stayed in charge and the GPU helped occasionally. But here is the 2026 reality. For AI workloads, the GPU is no longer the accelerator. The GPU is the primary processor. The CPU's role has changed. Today, the CPU prepares data, launches GPU kernels, handles coordination and I/O. Meanwhile, the GPU does the real work: model training, inference, matrix manipulations, attention mechanism. If CUDA did not exist, this shift would not be possible. CUDA is what allows us to treat the GPU as a programmable compute engine not just a graphics card. And that's why learning CUDA today is not about graphics or gaming. It is about understanding how modern computing actually works. Imagine you have to chop 10,000 onions for a giant festival. The CPU is like a world class executive chef. He is incredibly smart and can follow a complex 50 step French recipe perfectly. But he only has two hands. He chops the onions himself. It will take him all week. CUDA is the system that allows the chef to hire 5,000 junior cooks, that is the GPU in our context, give them each a knife and tell them all to do one simple thing at the exact same time: chop. In the early days of GPU programming, pre 2022, it was like building that skyscraper by hand forging every single steel bolt. To get the building to stand, you had to be a master blacksmith. In our world, that meant you had to be a C++ expert. The problem with the old way, pre to 2022, if you wanted the GPU to do math, you had to write long, complex C++ code to tell every single thread exactly where to stand and how to move. If you made one tiny mistake in your C++ code, the whole building would fall over. It was powerful, but it took months to build anything new. The transition, the power tool era 2022 to 2025. As we moved into the Hopper era, NVIDIA gave us power tools, the transformer engine. We stopped forging bolts and started using high powered drills. We still used C++, but the hardware started helping us do the heavy lifting automatically. The modern era, that is in 2026, and tensor native construction now in 2026 with the Blackwell B200, we have moved to prefabricated construction. The old way, managing 5,000 workers with individual hammers. The 2026 way, using a crane to drop an entire pre built floor into place. This is the qtile paradigm. Instead of writing hundreds of lines of C++ to manage individual workers, you use Python to tell crane where to drop the tile, the pre built floor. The result, you get the same skyscraper, but you build it in days instead of months, and it's stronger than ever before. If our software is the blueprint for a skyscraper, the NVIDIA Blackwell B200 is the heavy machinery that actually moves the steel. In the past, we had single chips that were like individual cranes, but the Blackwell B200 is a super chip. It's actually two massive chips joined together so tightly that your code does not even know they are separate. It's like having a crane with two arms that move in perfect synchronization. Now that we have seen the heavy machinery, the B200, how do we actually give it instructions? In 2026, we use CUDA 13.1. Think of this as the ultimate universal blueprint. In the old days, you needed a different set of plans for a house versus a skyscraper. Now, with CUDA 13.1, the code you write on your laptop for a small robo is the exact same code that runs on a $1 billion AI supercluster. It is write once, run everywhere for the first time in GPU history. Let us talk about the biggest headache we have removed: manual thread calculation. If you look at the old way, developers used to have to do complex mental math calculating coordinates. The messy math of moving that data into the GPU's ultra fast shared memory is now handled by the compiler. You define the shape, the system handles the sweat. Performance Python with C++ is built. This is the holy grail for us. Usually, if you want speed, you use C++, which is hard. If you want ease, you use Python, which is slower. But with the Qtile Python DSL, the gap has closed. Because the Blackwell chip is tensor native, it understands these tiles perfectly. You can now write a kernel in simple Python that runs just as fast as the elite hand-tuned C++ code. In summary, we can say the CPU is optimized for latency, handling complex logic and sequential tasks with a few powerful cores. The GPU is optimized for throughput, using thousands of simpler cores to perform the same computations in parallel. Earlier, GPU acted as accelerators, but by 2026, the GPU has become the primary processor for AI workloads. CUDA enables this shift by making GPUs fully programmable for general purpose computing.